Our next presentation is by Professor Olek of Purdue University on opportunities for customization of concrete structures using 3D printing.
Thank you, Narayan. Good morning, everyone. Narayan mentioned 4 continents. He never mentioned the American continent. Considering that we have snow outside, coming from Indiana, it feels like I'm from South America. But anyway, I'm glad that you guys made it here. And what I'm going to share with you is some of the work that we are doing on the architecture of the 3D printed elements. Particularly, I'm talking about the internal architecture. And one of the things that we are struggling as a group with is nomenclature. The nomenclature in this area really doesn't exist. It's being developed as we are working on developing some of the materials for those applications. So hopefully that will be one of the, if that technology were to develop further, as I hope it will, that will be one of the areas that needs to be brought up to speed with respect to how do we communicate to make sure that we are talking about the same things. I wanted to acknowledge my co-authors. Reza Moini is a PhD student working on it. Professor Zavattieri and Jeffrey Youngblood are my colleagues. We have a National Science Foundation grant that is focusing on the issue of internal architecture, 3D printing elements, and that's what I will talk about in the second part of the presentations. I wanted to start by highlighting some of the opportunities with 3D construction printing. And one of the obvious ones is, to me at least, is the freedom of design. You can, in principle, if you have a good control of the process of printing, you can print any shape, within reason, of course, that would be architecturally pleasing, and hopefully it will be cheaper to construct because you don't need to build sophisticated formwork in order to be able to print it. It was already mentioned partially by Victor in his presentation that the quality of the work and the shortage of the workforce that is skilled enough to build quality construction may be positively aided by using 3D printing. You can have a higher precision. Reduction of waste is one of the elements that is being commented on or brought about in connection with 3D printing. And I'm not entirely sure about the faster completion time at this point. I wouldn't say that that's really a driving force for it, but if we have fully integrated automated system of construction that also includes 3D printing, that potential is certainly there. As a couple of examples of the complex and unique structures, I've been to the conference on digitally printed concrete in Switzerland. It was first international conference sponsored by RILEM in September of last year. And we got the opportunity to see some of the nice architecturally pleasing elements that they were building there. Interestingly enough, this is not 3D printed. This is using a formwork that was 3D printed, okay? So they used a formwork that was 3D printed, and they cast essentially a conventional concrete mixture with proper rheological and properties and so forth. And they created something that is very architecturally, aesthetically pleasing, I think. Current state of the 3D printing construction is really variable. It's a very dynamic field. It's still evolving. There are a handful of companies all over the world where you have various attempts to create 3D printing structures, and there are some of the bigger players that are listed here, but literally that changes from month to month. Some of those companies appear and disappear as quickly as they appeared. Some of them are actually making quite a bit of progress. This is as of last year. You can see this graph that shows the exponential increase in the number of publications and projects that are focused on 3D printing. So in the last few years, we really have a pretty dramatic increase in interest and in output. And with the funding coming in, at least in Europe, in some other parts of the world, I think that great progress is going to be made. The indication of the strength of the interest is also listed on this slide. There are several companies that either actively participate in sponsoring various 3D printing projects, or sponsoring the universities or research organizations, or they actually have their own R&D in that area, Sika being one of them, for example. So whenever we have companies that come to the table, they typically bring some money, and are also interested in getting something that is tangible to get the return on their investment. So that helps certainly with the development of the technology. I borrowed this slide from one of the presenters at the meeting in Switzerland, and he kind of compared the stages in the product development with the stages in humans' life, if you will. So, you know, we are born, and then we grow, we mature, we have a high level of productivity, and then, you know, we get old and the productivity declines, right? And the audience is listed here on the vertical axis, and you can see what's happening during those various stages. And if you were to put a box around where we are right now, we are really in the introductory period, and maybe slightly in the area of growth. But what is associated with this, that our audience is primarily innovators, right? People who really have a passion for this technology and try to innovate and make changes. The market is very small. In fact, it's difficult to identify the market. The industry comes to the table and say, where can we use it? Or, you know, we would like to print a wind turbine, for example. Can you help us to do that? You know, there's a myriad of obstacles before one can move to that stage. But the industry certainly comes with projects they identify as projects that might be useful or interest for them. Since everything is prototype at this stage, the prices of equipment and the technology itself is quite high. Sales, hard to talk about. If you go online and try to buy a 3D printer, you can actually find the places that will tell you that you can buy a 3D printer. We contacted several of them. We wanted to buy a 3D printer, and we cannot buy a 3D printer. And not only because we don't have the money, because nobody actually can sell you a 3D printer at this point, right? In terms of a business plans, you know, there is an awareness among the groups that are dealing with it, but there is really no growth opportunities very strongly identified. You know, so when we hear about the 3D printing, there is important that we keep the awareness of what is true, what is myth, and what is the reality. So again, I borrowed this from Len Niels, who is the head of 3D Printers company in Denmark, which, as I learned today, actually did produce a 3D printer that they sold to my colleague in Belgium. But you know, he was saying that if you go and watch the YouTube, you will see this yellow house, and I'm sure each of you saw the video. And they say we printed in 24 hours, and it cost $10,000. Well, it took them from October of 2016 to February 2017 to actually print it, and the cost was actually much more higher than that. But when they posted that video, it created such a high traffic that they had to, on their webpage, they had to stop responding to the request for giving the interviews or talking to the clients, because they weren't simply ready to do that. You know, the guy from Tennessee called on Monday and he says, I want the house by Wednesday. I said, what do you mean you want the house by Wednesday? Well, you said 24 hours, I'll give you $10,000, right? But it's not happening. So, you know, there was a lot of talk a few months ago about Dubai committing to building an office building that will be entirely printed in 3D. In reality, the most important elements of that office were printed in China, shipped to Dubai, and they were assembled on site. So It's important to keep that in mind because the reality of actual implementation of those technologies is still in the very early stages. In other words, we are at the baby stage. We are crawling, not even walking yet. The other thing is economy of the whole process. If we start thinking about printing houses, printing the elements like walls, it's only about 35% of the total cost of the building, and you can see the associated costs over there. And even with this, we are only able, to some extent, do a very basic, replacing the masonry. You've heard from Victor, right? We don't know what to do with reinforcement. We don't know how to do overhangs. We don't know how to do roofs. How do you install the roof on a 3D printed house? So again, that will have to be part of the integrated 3D construction process. As with any new technology, you also have some very different areas of interest and focus. If you talk to the industry people, cost and time is the most important thing for them. And they want to know how to make this technology to happen. Right? So going to the concept of digital fabrication and intricacies of what the extrusion process and the rheology involves is not what the industry is thinking about. Researchers, we tend to think about what is happening on the materials level, how the materials behaves, how the rheology is changing, how that influences the properties. Being in academia, cost of the actual construction is never serious concern, right? We are so focused on getting the equations right and making sure that we have the models right that eventually we kind of figure out that maybe the industry will come up with workable and economical solution. So somehow those two trends have to converge at some point. There are some important missing pieces in the process, in this whole technology. Probably the most important one, and we hear a lot about it at ACI. There is ACI formed a committee on 3D printing, and one of the tasks that the committee is dealing with is what do we do about compliance with the building codes? Those are very different structures, and we do not have existing building codes that can address some of the issues of the quality of the concrete or quality of the structure with the 3D printed concrete. I already mentioned the issue of reinforcement, multiple floors, roofs. Some people think that 3D printing technology would be great for high rises because you will avoid, for example, connections between the beams and walls, which are always the weak point of this kind of structures if you can have a continuous printing. But how do we reinforce those, right? So there is a problem. What do you do with the overhangs? If the condition changes at the construction site, how do you adapt? You may have a mix optimized for a given conditions, and then the conditions do change. There's warmer or colder day, there's a different wind. Do we have a good knowledge of what we are going to do with it? And how do we handle that? And we need those basic rheological and materials research resolved because we can move before we can move further. Durability is another big problem. That if you do layer by layer printing, you have naturally occurring cold joints, essentially, interfaces that will have different properties. There's lack of continuity there. How do they influence the behavior of the element? So that's one of the areas of research that we are specifically focusing on. We are looking at the role of interfaces and how those interfaces, heterogeneities introduced by those interfaces, how do they influence the behavior? And there are various approaches. Of course, one of the approaches is that you realize that there are weak points and design your building to account for that. The other approach might be that you control where those weak points do occur because you have a good control of the how you deposit the individual layers, and maybe by using the control of the weakness of the interfaces, you can produce something that is actually useful. So that's what I wanted to share with you a little bit. So we are approaching this from the point of view that if we look at the issue of controlling the internal architecture, in other words, the arrangements of the individual filaments in space, if we consider the microstructure that results from that arrangements, and the word of microstructure is we struggle with because we don't know what is the proper nomenclature for that. Microstructure means different things to different people. But I'm talking about the spatial orientation of the interfaces and what is the mechanical response to that. So we are looking at the architectural cement-based materials with control layout of the filaments and therefore control layout of interfaces and how they influence the properties. We are thinking that by combining those effects, you can actually change the behavior of otherwise brittle materials, and we have some results of that to share with you. So one of the things that we've done is we created a various type of concrete elements with different internal architecture, right? So this is a honeycomb kind of structure. Actually, this acts like a spring. You know, I couldn't make the video link work in here, but you know, if you squeeze it, it actually deforms elastically and bounces back. So you can think of it as being a sort of a concrete spring. No reinforcement, but it doesn't break. Or you can create what we call the Bulligan architecture, where you have each layer of filaments oriented with respect to the underlying layer by some degree that is different. And you can go to the entire spectrum. You are trying to find out what is the optimal orientation of those filaments in space that will force the propagation of the cracks to the interfaces in the direction that you want it to propagate. And we got some results that are quite encouraging. So you can see that we have curves, load versus the displacement, and you can see that we have various architectures there. You know, the Bulligan structure was 45, 8 degrees solid, 60% infill, and so forth. You can see that some of them actually are capable of quite a big displacement and a considerable amount of sort of a soft failure past peak performance. If you look at the area under this curve, there's an indication of the toughness of the structure, and you can see that by changing some of those parameters, you can actually increase the toughness, you can increase the fracture resistance, and you can make a brittle material sort of quasi-brittle material that is a little bit more flow tolerant than the material that you will cast. We spent some time trying to analyze what the influence of the changing of this internal architecture has on the porosity of the structure. To what extent can we predict where the pores are going to be, and can we take advantage of the location of those pores with respect to predicting the mechanical properties? So we've done some micro-city characterization of those elements, and one of the things that I would like to show here is that you can see that those are the individual filaments, and you can see even in this picture that even though we ideally try to place one filament on top of the other, there will be always some movement, internal movement of the filaments that actually displaces the zone of the interfaces in the location that you didn't initially thought that that zone would be located at. And we've done some analysis and observed some of the locations of the cracks, and it turns out that we actually have two types of internal inhomogeneities. There's one that is definitely related with the interface, both in the horizontal and vertical directions, but there are also there's another series of imperfections that are in the core or in the plane that goes through the cores of the individual filaments. And depending how big of the filament it is that you are trying to extrude. And depending what is the what are the rheological properties of that, there is, because of the some of the fluidity-related issues, you may have some shearing of material in various layers that will actually result in the core, and I'm talking about the core of the filament, having different densities and different porosities than the regions near the interfaces. There will be also quite a bit of, at least in our experience, there was quite a bit of unreacted cement particles that were at the interfaces. This is related to different level of evaporation that happens at those locations. If you compare the printed element with the cast element, you will see that by the printing process, you are aligning the defects, if you will. And the question then is, are we going to live with this alignment of defects, or are we going to change it in predictable way so they are becoming a little bit more dispersed and not aligned, because that definitely will increase or introduce some level of weakness into some of those elements. So I will skip some of that in the interest of time. What I wanted to show you is that we have the shifting of the filaments. You can see it more exclusively here, and that influences the internal porosity. That changes the nature of these interfacial zones. If you look at this as a close-packed structure, from this diamond type of the opening to more of a triangular forms of openings that you see over here. And interestingly enough, you don't actually see that on the outside of the element. We printed the cubes that were about 1 inch by 1 inch by 1 inch, and from the outside they looked pretty good, but when we look inside, we've definitely saw this shifting. So it's related to both forces, the gravity, but also changing rheological properties with time. If you compare the printed element with the cast element, in the cast element you have randomly distributed pores, but you have pores that are, I call it patterned network, because they are following, obviously, the direction of the printed filaments. So those are some of the conclusions that we got from doing CT scans. So we have a variety of pores that are in the interfacial regions, but they're also in the cores of the filaments themselves. And the most important probably conclusion is the pore network follows the architectured pattern that we put in. So we have those processing-induced heterogeneities that change the porosity of that system. And I think there's an opportunity for us to take advantage of those predictable locations of those pores to change the mechanical response. So the question is, where do we go from here? Well, I think the next big thing is really to start looking at the reinforcement. Some of the work that we are doing right now, we are looking at the steel wires that is encapsulated in the epoxy that is printed at the time, around each of the wires at the time of development of the material, of the reinforcement. So essentially we are sort of looking at the almost like a pre-stressed cable, but it will be more stiff because it will be having this jacket of epoxy around each of the wires, and see how that will perform as the reinforcement. The thing is that you can feed the continuous wire and you can print the epoxy at the same time as you are printing concrete. But that's a challenge because that requires rethinking the entire material system. How do you make cement or cementitious system more tolerant to the increased heat caused by the fact that you are trying to print hot epoxy around the wire? You would have to change maybe the process, how you deliver the material. Do you mix it at the nozzle or do you mix it ahead of time? And this is pretty much all I think I have to say. I'm not sure how I'm doing on time, but I'm pretty sure I'm pretty close to my time limit. This is the team that I wanted to acknowledge, and if you guys have any questions, I will try to answer them. Thank you.
Thank you, Jan. Very interesting presentation. It's important what you do here to try to understand the microstructure. And once we understand, we can try to tailor it. That's very fundamental, and I support this. Now, please allow me to make some comment on what you said about buying 3D printers. Of course, it's not easy. What you said, no one can sell you a printer. In Europe, we had the first case, a European tender for a large-scale printer. This was in a national project with a lot of industrial partners, with European support also, European Fund for Regional Development. So we sent out a tender. We had 3 companies proposing their concepts. Only one of them was in line with the technical requirements, and that one was delivered and installed, and it was presented to the press last week, and even ACI mentioned it in the newsletter last week. So this is a gantry printer, a very large scale, so we can print a 2-story high building with that. So within 5 or 6 months, I think we will print it. So yes, you can buy it, but it's not easy for sure.
Right, thank you. Thank you.